What if everything you thought you knew about the universe was wrong? What if reality itself was a carefully constructed illusion, a fragile web of laws and principles waiting to collapse? The cosmos is vast, too vast to comprehend, and filled with secrets so disturbing they could shake the very foundation of human understanding. For centuries, scientists and philosophers have wrestled with questions that seem to defy logic. Some of these mysteries are playful riddles, puzzles to be solved with enough intelligence. But others? They aren't just strange. They're terrifying. They suggest that our existence is fleeting, that the universe is far more hostile than we dare to imagine, and that at any moment, everything could change. Tonight, we're diving into the most unsettling theories about the universe. Ideas that will challenge what you believe about reality, time, and even your own consciousness. These aren't just thought experiments. They're real scientific paradoxes and hypotheses that have left some of the world's greatest minds speechless. From the eerie possibility that you're nothing more than a temporary flicker of self-awareness, to the unsettling idea that an unstoppable cosmic event could wipe out everything in an instant. These theories aren't for the faint of heart. But maybe, just maybe, the most disturbing part isn't the theories themselves. It's the possibility that some of them might actually be true. Chapter 1. The Boltzmann Brain Hypothesis. Imagine waking up one day and realizing that everything, your memories, your experiences, your entire life, was a lie. Not just a simple deception, but an illusion created by pure chance. What if, instead of being born and growing up in a real, continuous universe, you were nothing more than a brief spark of self-awareness floating in the endless void? A momentary flicker of thought that would disappear as suddenly as it emerged. This is the horrifying premise behind the Boltzmann brain hypothesis, one of the most unsettling ideas in modern physics and cosmology. It suggests that, statistically speaking, it's far more likely that you are a disembodied, spontaneously generated brain with false memories than a real person living in a stable universe. The implications of this theory are nothing short of mind-shattering, because if it's true, then everything you believe about existence could be an illusion. The theory traces its origins to Ludwig Boltzmann, a 19th century physicist who was instrumental in the development of statistical mechanics. Boltzmann's work helped explain how disorder, or entropy, naturally increases over time, a concept that later became the foundation of the second law of thermodynamics. He theorized that, given enough time, even the most chaotic systems could spontaneously arrange themselves into temporary moments of order, simply by random chance. Boltzmann used this idea to explain why the universe appears to be highly ordered, despite the natural tendency toward disorder. His argument was simple. If we wait long enough, random fluctuations in an otherwise chaotic universe could produce small pockets of low-entropy environments, like our own observable universe. But this idea led to a disturbing question. If such fluctuations could create entire universes, could they also create individual conscious minds? According to Boltzmann's logic, the odds of an entire structured universe forming from randomness are astronomically small. However, the odds of a single, self-aware brain forming out of pure chance are much, much higher. After all, forming a fully functioning human brain for just a moment requires far less order than forming an entire universe filled with galaxies, planets, and physical laws. This means that, statistically speaking, it is far more likely that you are a spontaneously generated Boltzmann brain than a real human living in an ordered, long-lasting universe. In other words, there is a terrifying possibility that right now you are nothing more than a fleeting, self-aware brain that just happened to pop into existence with fully formed memories, an entire fabricated past, and a false sense of reality. And just as suddenly as you appeared, you could disappear back into the void. The Boltzmann brain problem creates a paradox. If the universe were infinite and governed by the principles of entropy, then the overwhelming majority of conscious experiences should belong to Boltzmann brains, rather than biological beings who evolved in a stable universe. This suggests a deeply unsettling conclusion, that rational beings should not trust their own memories or perceptions, because they could all be artificially constructed by random quantum fluctuations. Even worse, if you are a Boltzmann brain, there is no guarantee that your experience of reality will last more than a fleeting moment. You might blink out of existence before you even finish this sentence. Or, just as chillingly, you might continue to exist indefinitely, drifting alone in an empty cosmos, trapped in an endless cycle of hallucinations and false memories. The Boltzmann brain hypothesis has profound implications for both physics and philosophy. If the theory is correct, it undermines the very foundation of scientific reasoning. After all, if we cannot trust our perceptions and memories, how can we trust the scientific method itself? How can we prove that our universe is real and not just a temporary statistical anomaly? Moreover, this hypothesis raises an even deeper existential question. If we are Boltzmann brains, does anything matter? If the universe is nothing more than a random fluctuation that will eventually dissolve back into chaos, then every thought, every emotion, every moment of joy or sorrow might be utterly meaningless. Thankfully, not all scientists accept the Boltzmann brain hypothesis as a legitimate concern. Many argue that for Boltzmann brains to vastly outnumber real observers, the universe must be infinite and governed by random fluctuations, a claim that is still unproven. One of the strongest counter-arguments comes from cosmological inflation theory, which suggests that our universe emerged from a rapid expansion event rather than a random fluctuation. If this is true, then our cosmos is not just a temporary statistical anomaly, but a structured reality with genuine history and evolution. Additionally, some physicists propose that consciousness itself cannot arise from random chance alone. They argue that self-awareness is a product of sustained interactions with a stable environment, which means that a true Boltzmann brain, one that genuinely experiences and interprets reality, might be an impossibility. Even if the probability of being a Boltzmann brain is low, the mere fact that this theory exists raises unsettling questions about the nature of reality. If we cannot prove that we are not Boltzmann brains, then how can we ever truly trust our own perception of the world? Perhaps, at this very moment, you are nothing more than a transient bubble of thought in an infinite void. Maybe, as you listen to this, you are already beginning to dissolve, your memories unraveling, your sense of self slipping away. Or perhaps, against all odds, you are real. And the universe you see around you isn't just a fleeting hallucination, but something far more remarkable. An actual, ordered reality that will continue long after this moment ends. But how can you ever be sure? Chapter 2. The Dark Forest Theory. Imagine standing alone in a vast, silent forest at night. The air is thick with tension, and the darkness stretches endlessly in all directions. Nothing moves, nothing makes a sound. The silence is not comforting, it is oppressive. Something is out there, unseen, unheard, and it is choosing to remain hidden. But why? This is the essence of the dark forest theory, a chilling answer to the Fermi paradox. The unsettling question of why, in a universe filled with billions of habitable planets, we have found no evidence of intelligent extraterrestrial life. The theory suggests that alien civilizations are not absent, but deliberately silent, hiding in fear of an unseen threat. The universe, rather than being a grand cosmic community, may instead be a battlefield where survival depends on staying undetected. The Fermi paradox is named after physicist Enrico Fermi, who famously asked, "Where is everybody?" Given the vastness of the universe and the high probability of habitable planets, it seems mathematically inevitable that intelligent civilizations should have emerged long before humanity. And yet, despite decades of searching, there is nothing. No signals, no probes, no artifacts, just an overwhelming silence that stretches across the stars. The dark forest theory, popularized by Chinese science fiction writer Liu Cixin in the Three Body Problem series, presents a grim interpretation of survival in the cosmos. It suggests that the universe is filled with civilizations, each aware that others might exist, yet forced to act with extreme caution. In this scenario, trust is impossible, and the safest course of action is to remain hidden, or strike first before being discovered. This terrifying logic is built on a few fundamental ideas. Survival is the primary instinct of any intelligent species, and the motivations of others can never be truly known. A civilization that seems peaceful today could become a threat in the future, and there is no way to predict its evolution. Because of this uncertainty, the only rational strategy is silence. Those who fail to remain undetected risk drawing the attention of an entity that sees them as a potential competitor, a risk that could lead to extinction. Unlike many other solutions to the Fermi paradox, the dark forest theory does not require aliens to be fundamentally different from us. It is based on the same survival instincts and competitive behaviors seen throughout human history. The universe may not be empty or filled with friendly explorers. It may be a graveyard of civilizations that spoke too loudly and were wiped out by those who remained silent. The eerie implication is that countless advanced societies could exist, yet all of them have learned the same lesson. Do not reveal your presence. This would mean that every signal sent into space, every attempt to reach out, could be an invitation to disaster. If extraterrestrials have encountered this dilemma before, then they may have already taken action against civilizations that unknowingly exposed themselves. If the dark forest theory holds true, then the most advanced civilizations are the ones that have mastered the art of concealment. The key to survival is not expansion or exploration, but vanishing into the cosmic shadows. Instead of sending signals, they listen. Instead of seeking alliances, they wait. Instead of trusting, they assume the worst. This would explain the great silence we observe. It would mean that intelligent species exist, but they are deliberately avoiding contact. Some may have even chosen to eliminate potential threats preemptively, ensuring their own survival by eliminating others before they have a chance to act. The most successful civilizations may not be the ones that grow and thrive openly, but the ones that erase all traces of themselves, ensuring they are never found. The dark forest theory is closely linked to another unsettling idea, the Great Filter. This concept suggests that there is some universal challenge that prevents civilizations from advancing beyond a certain stage. Some believe this filter could be the difficulty of developing complex life, the self-destructive tendencies of intelligent species, or even a natural disaster on a cosmic scale. But what if the great filter is not an internal threat, but an external one? What if the real reason we see no other civilizations is because something, or someone, ensures they never reach an advanced stage? If this is true, then the silence of the cosmos is not just a mystery, but a warning. A troubling question arises from the dark forest theory. If extraterrestrial civilizations exist, and they are aware of us, have they already made their decision about what to do with us? For over a century, humanity has been broadcasting signals into space. These signals, carrying our music, our broadcasts, and our presence, travel at the speed of light, reaching farther into the universe with every passing year. If someone is listening, they may already know we exist. The real question is whether they consider us a threat. If an advanced civilization adheres to the principles of the dark forest, they may not wait for us to reach them first. They may have already determined that any emerging species could one day pose a danger and taken steps to ensure we never get that chance. If so, we might not even see it coming. For decades, projects like SETI, Search for Extraterrestrial Intelligence, have been listening for alien signals, hoping for first contact. Some scientists have even suggested actively sending messages to announce humanity's presence. But if the dark forest theory is correct, then this could be one of the most reckless decisions in human history. Renowned physicist Stephen Hawking cautioned against making contact with extraterrestrial civilizations, warning that any sufficiently advanced species might not be benevolent. History shows that encounters between vastly different civilizations on Earth have often ended in disaster for the less advanced party. If the same logic applies on a cosmic scale, then humanity's eagerness to reach out could lead to its downfall. If survival depends on remaining unnoticed, then the safest course of action is clear. Stay silent. Listen, but do not speak. Observe, but do not announce. Because once our presence is known, we cannot predict who or what will hear us. The dark forest theory paints a vision of the universe that is both unsettling and logical. Rather than a place of discovery and cooperation, it may be a realm of fear and paranoia. It suggests that civilizations do not thrive in openness, but in secrecy. That the cosmos is not empty, but filled with unseen watchers, hidden societies, and the ever-present danger of making a sound in the wrong direction. Perhaps the reason we have found no evidence of extraterrestrial life is not that it does not exist, but that it has learned a truth we have yet to accept. In a universe where survival is the ultimate goal, the only safe strategy is silence. Chapter 3. The False Vacuum Hypothesis. The universe, as vast and eternal as it may seem, might be teetering on the edge of an apocalyptic shift, one that could erase everything in an instant. Not with a bang, not with a whimper, but with a silent and unstoppable wave of destruction, rewriting reality itself. This is the nightmare lurking within the false vacuum hypothesis, a theory that suggests our universe may not be in its most stable form, and that at any moment it could collapse into something entirely different. To understand the false vacuum hypothesis, we must first understand what physicists mean by a vacuum. In quantum field theory, a vacuum is not simply empty space. It is a state of energy, and not all vacuums are created equal. There exists the possibility that our universe is currently in a false vacuum state, meaning it is stable enough to exist as it does, but not in the most stable configuration possible. A more stable state, a true vacuum, could exist, and if even the smallest patch of true vacuum were to form anywhere in the cosmos, it could trigger an irreversible chain reaction, consuming our entire universe in an instant. This is not science fiction. It is a legitimate concern derived from our current understanding of particle physics. Theoretical calculations suggest that our vacuum state, dictated by the Higgs field, may be metastable. If this is true, then everything we know, the galaxies, the stars, the laws of physics themselves, could one day be rewritten, or worse, obliterated entirely. The terrifying aspect of a false vacuum collapse is that we would never see it coming. If somewhere, deep in the cosmos, a fluctuation caused a bubble of true vacuum to form, it would expand outward at the speed of light. There would be no warning, no observable signs. One moment, everything would be as it is, and the next, the fundamental structure of reality itself would be rewritten. Planets, stars, black holes, even the very forces of nature that govern our existence. All of it would be replaced by something unrecognizable, or perhaps by nothing at all. Unlike cosmic disasters that take billions of years to unfold, like the slow death of stars or the expansion of the universe, a false vacuum decay would be instantaneous and absolute. The laws of physics themselves might cease to function in ways we can comprehend, making survival not just unlikely, but impossible. The good news, if one can call it that, is that while the false vacuum hypothesis is a serious theoretical possibility, the odds of such a catastrophe occurring any time soon are incredibly small. The universe has existed for billions of years without such an event, suggesting that if we are in a false vacuum state, it is at least a relatively stable one. However, some physicists speculate that high-energy events, such as those occurring in the cores of neutron stars, or even within advanced particle accelerators, could theoretically trigger a vacuum collapse. While highly unlikely, the mere possibility raises questions about how little control we have over the fundamental nature of reality. If the false vacuum hypothesis is true, then the universe we live in is not the ultimate reality. It is a temporary construct, a cosmic bubble waiting to pop. It suggests that everything we consider fundamental, from gravity to time itself, is just a precarious arrangement of quantum fields that could, at any moment, be rewritten by an unseen and inescapable force. So, if the universe truly is a false vacuum, what lies beyond? Is there a higher, more stable state of existence waiting on the other side? Or would the collapse erase everything, leaving behind a void beyond comprehension? The only certainty is that, if it happens, we will never know. One moment we are here, and the next we are gone. And perhaps, somewhere out there, the first whisper of the true vacuum bubble has already formed, racing toward us at the speed of light, unseen and unstoppable. Chapter 4: The Black Hole Information Paradox. Black holes are among the most mysterious and terrifying objects in the universe. They devour everything that crosses their event horizon, crushing matter and warping space-time itself. But there's one question that has baffled physicists for decades. What happens to the information of everything that falls into a black hole? The answer to this question has led to one of the most perplexing paradoxes in modern physics, the black hole information paradox. A black hole's event horizon is a point of no return. Once something passes this invisible boundary, it is forever lost to the outside universe. According to classical physics, all the information about the fallen object should be lost as well, reduced to nothing more than mass, spin, and charge. an idea captured by physicist John Wheeler's famous phrase, "Black holes have no hair." But this contradicts a fundamental principle of quantum mechanics. Information cannot be destroyed. In the quantum world, every interaction leaves an imprint, a record of what has occurred. If black holes erase information, it would violate the very fabric of quantum physics, creating a paradox that threatens our understanding of reality itself. In 1974, physicist Stephen Hawking made a groundbreaking discovery. He proposed that black holes aren't entirely black. They emit a faint glow of thermal radiation, now known as Hawking radiation. This radiation is produced by quantum fluctuations at the event horizon, where pairs of virtual particles appear and annihilate each other. Sometimes one particle falls into the black hole while the other escapes, carrying away a tiny bit of energy. Over time, this process causes the black hole to shrink and eventually evaporate completely. But this only deepens the paradox. If a black hole disappears, what happens to all the information it consumed? Does it simply vanish, defying the rules of quantum mechanics? Or is there a hidden mechanism preserving it in ways we don't yet understand? One controversial solution suggests that black holes don't just erase information, they destroy it violently. This idea, known as the firewall hypothesis, proposes that the event horizon is not a smooth boundary, but a searing wall of high-energy radiation. Any particle, or unfortunate astronaut, approaching the event horizon would be incinerated instantly, reducing everything to meaningless noise. But this contradicts another well-established principle of physics, the equivalence principle, which states that falling into a black hole should feel no different than drifting through empty space. If the firewall exists, it means that general relativity and quantum mechanics are in direct conflict, and one of them must be wrong. Another mind-bending resolution to the paradox comes from an idea known as the holographic principle. This theory suggests that all the information that falls into a black hole isn't lost at all. It is encoded on the event horizon itself, like a cosmic hard drive storing every detail of the objects that have fallen in. This idea implies that the universe itself might work in a similar way, that everything we experience in 3 dimensions is actually a projection of information stored on a distant surface. If true, reality as we know it could be nothing more than a vast, complex hologram. Some physicists believe that the solution to the paradox lies in the strange world of quantum entanglement. When 2 particles become entangled, they remain connected no matter how far apart they are. Some theories suggest that black holes use this mechanism to teleport information elsewhere in the universe, possibly through hidden wormholes connecting different points in space-time. This raises the possibility that information isn't lost, but is simply transferred somewhere beyond our current understanding. If black holes are cosmic gateways rather than ultimate dead ends, then the implications for space travel and the nature of reality itself are staggering. The black hole information paradox remains one of the greatest unsolved mysteries in physics. It challenges our deepest assumptions about the universe, forcing scientists to reconsider the very foundations of space, time, and information. Whether the answer lies in holography, firewalls, or some yet undiscovered principle, one thing is certain. Understanding black holes may hold the key to unlocking the true nature of the cosmos. And, as we continue to probe the depths of these enigmatic objects, we may discover that reality itself is far stranger than we ever imagined. Chapter 5. The Great Filter Hypothesis. The universe is vast beyond comprehension, filled with countless galaxies, stars, and planets that seem to suggest intelligent life should be common. Yet, as far as we can tell, we are alone. This eerie contradiction between the high probability of extraterrestrial civilizations and the complete lack of evidence for them is known as the Fermi paradox. One of the most sobering explanations for this paradox is the Great Filter hypothesis, a concept that suggests there is an invisible barrier preventing most, if not all, civilizations from advancing beyond a certain point. The question that haunts us is, have we already passed this filter, or is it still ahead, waiting to end our existence? The Great Filter is an unknown event or process that drastically reduces the number of civilizations capable of developing interstellar travel or long-term survival. It is the reason why, despite the overwhelming number of potentially habitable planets, we do not see evidence of extraterrestrial life. If the filter is behind us, it means that intelligent life is incredibly rare, and we are among the lucky few to have made it this far. But if the filter is ahead of us, it suggests that almost every advanced civilization ultimately destroys itself before reaching the stars. The Great Filter could exist at various points in a civilization's evolution, eliminating most life forms before they have a chance to spread beyond their home planet. Some of the proposed stages include the origin of life. It is possible that the formation of life from non-living matter is an extremely rare event, requiring conditions that almost never occur. If this is the case, then we are already incredibly lucky to exist at all. The emergence of complex life. While simple microbial life may be common, the leap to multicellular organisms could be the true bottleneck. Many planets may be teeming with bacteria-like life forms, but very few may ever develop into something more complex. Intelligence and tool use. Even if complex life does arise, the ability to develop intelligence, technology, and a civilization capable of altering its environment may be exceedingly rare. Avoiding self-destruction. Perhaps the most terrifying possibility is that intelligent civilizations inevitably self-destruct before achieving interstellar travel. War, environmental collapse, artificial intelligence, or unforeseen existential threats could be the doom of every advanced species. The unknown doom. There may be catastrophic cosmic events we have not yet discovered, such as gamma-ray bursts, rogue AI, or self-replicating nanotechnology, that act as the Great Filter, eradicating civilizations before they become spacefaring. The implications of the Great Filter are profound. If the filter is behind us, it means that humanity has already beaten the odds and passed the most difficult hurdles. We could be one of the first intelligent civilizations to emerge, giving us the responsibility of preserving life and expanding into the cosmos. However, if the filter is still ahead, it means we are doomed to the same fate as countless civilizations before us, destined to disappear before we ever reach the stars. Scientists continue to search for signs of alien civilizations, hoping to determine whether we are alone or simply the latest in a long line of doomed species. Every silent sky and every failed search for extraterrestrial intelligence brings us closer to an unsettling truth. If we do not find evidence of others, it may mean that we are next in line to face the Great Filter. The Great Filter hypothesis serves as both a warning and an inspiration. If the greatest challenge is still ahead, humanity must be vigilant, ensuring that we do not fall victim to the same fate that may have erased countless others. If we have already passed it, then we may carry the unique burden of being the first species capable of breaking the cycle. Either way, our survival and expansion into the cosmos may be the most important endeavor in the history of life itself. Chapter 6. The White Hole Hypothesis. Black holes are often thought of as nature's ultimate traps, regions of space where gravity is so intense that nothing, not even light, can escape. But what if the universe also had their mirror opposites? Enter the white hole hypothesis, a concept that suggests the existence of objects that behave in the exact opposite way of black holes. Instead of pulling matter in, they spew it out, never allowing anything to enter. If white holes exist, they could radically reshape our understanding of time, space, and even the origins of the universe itself. A white hole is a theoretical region of spacetime that only allows matter and energy to exit, never to enter. In essence, it's the reverse of a black hole. While black holes are formed from the collapse of massive stars, leading to singularities where gravity becomes infinite, white holes would hypothetically be regions where nothing can ever collapse inward. Imagine an explosion frozen in time, continuously expelling matter without ever taking any in. The idea of white holes originates from the mathematical solutions to Einstein's field equations in general relativity. When solving for black holes, the equations also allow for a theoretical counterpart, a white hole, that, in theory, could exist alongside its darker sibling. However, just because the math allows it doesn't necessarily mean nature follows suit. One of the most intriguing aspects of white holes is their potential link to black holes. Some theories suggest that every black hole might be connected to a white hole on the other side, forming what we know as a wormhole. If this is true, then falling into a black hole might not mean being crushed into oblivion, but rather being expelled from a white hole somewhere else in the universe, or even in a completely different universe. This idea has led some physicists to speculate that white holes could explain the Big Bang itself. If our universe originated from a singularity that suddenly erupted with energy, it might have been the result of a white hole forming from the collapse of matter in another universe. In this way, every black hole could birth a new cosmos, creating a never-ending cycle of universes expanding and contracting across time. Despite their theoretical foundation, no white holes have ever been observed. They pose a major problem. They don't seem to be physically possible under normal circumstances. In order for a white hole to exist, it would have to have been created in a way that prevents it from ever collapsing into a black hole. Given how the universe operates, this seems almost impossible. However, some astronomers have proposed that certain gamma-ray bursts, intensely energetic explosions in deep space, could be the brief, violent signatures of white holes momentarily flashing into existence before vanishing. These bursts, which are among the brightest events in the cosmos, could be the chaotic remnants of a white hole briefly existing in our universe before self-destructing. One of the most profound implications of white holes relates to the nature of time itself. In physics, time appears to flow in one direction, forward. We experience past events leading to future ones, and never the other way around. However, the equations of general relativity don't necessarily impose a preferred direction for time, meaning that, theoretically, time could run backward just as easily as forward. Some have suggested that white holes could be examples of this concept in action. If black holes represent a forward flow of time, where matter is drawn in and information is lost, then white holes might be the reverse, where matter and information re-emerge, unwinding the destruction that occurred in a black hole. This would suggest that the universe might not be strictly moving forward in time, but rather oscillating between destruction and creation. Some radical theories propose that white holes might not be just isolated cosmic oddities, but instead could be responsible for one of the greatest mysteries in physics: dark matter. Dark matter is the unseen mass that makes up most of the universe's total matter content, but doesn't interact with light, making it invisible. A fringe hypothesis suggests that tiny primordial white holes, remnants from the early universe, could still exist, acting as gravitational sources that we mistake for dark matter. If true, this would mean that we've been detecting the gravitational influence of white holes without realizing it, misinterpreting them as an unknown form of matter. Whether or not white holes exist remains one of the great unanswered questions of cosmology. If they do, they could revolutionize our understanding of black holes, the origins of the universe, and even the nature of time itself. If they don't, they still serve as an important reminder that the universe may be far stranger than we currently imagine. For now, white holes remain a purely theoretical concept. But as our technology advances and our understanding of physics deepens, we may one day uncover evidence that these cosmic anomalies are more than just mathematical curiosities. They may be real, lurking somewhere in the vastness of space, waiting to be discovered. Chapter 7: The Simulation Hypothesis. Imagine waking up one day to discover that everything you've ever known, your thoughts, your experiences, even the physical world around you, is nothing more than a meticulously crafted illusion. What if reality, as we perceive it, is just an intricate simulation, an elaborate program running on an incomprehensibly powerful computer, created by an advanced civilization? This is the essence of the simulation hypothesis, a concept that suggests our universe isn't the true base reality, but a carefully constructed artificial environment. The idea that reality might be an illusion is not new. Philosophers have speculated for centuries about the nature of existence, from Plato's allegory of the cave to René Descartes' famous assertion, "I think, therefore I am." But the modern form of the simulation hypothesis gained traction thanks to Nick Bostrom, a philosopher at Oxford University. In 2003, Bostrom proposed a groundbreaking argument. If a technologically advanced civilization could create highly realistic simulations, it is statistically more likely that we are living in one rather than in the one true base reality. Bostrom's argument is based on probability. If civilizations in the future can generate millions or even billions of simulated worlds, then the number of simulated conscious beings would vastly outnumber those in the base reality. In other words, if it is possible to create such simulations, it is overwhelmingly likely that we are inside one. Although it might sound like science fiction, some scientists and thinkers believe there are signs that our universe behaves more like a programmed environment than a physical reality. Physics has fundamental constraints, such as the speed of light being the maximum speed limit of the universe. Some researchers have speculated that these limitations could resemble the constraints of a computer program, akin to processing limits in a simulation. Moreover, quantum mechanics has revealed strange behaviors at the smallest scales. Quantum entanglement allows two particles to instantaneously affect each other, regardless of distance, while the observer effect suggests that reality behaves differently when it is being measured. These oddities might be signs that our reality is rendered on demand, just as a video game generates only what is necessary when a player interacts with it. One of the most compelling arguments for the simulation hypothesis comes from information theory. The universe appears to be composed of discrete units, like pixels in a video game. Scientists have discovered that space, time, and even energy seem to be quantized, broken into the smallest possible units. This is reminiscent of how digital systems work, using individual bits of data to create a seamless experience. Some researchers, like physicist James Gates, have even found what appears to be computer code embedded in the fabric of reality, error-correcting codes similar to those used in digital communications. If reality were truly continuous and analog, such a structure would not be expected. If the universe is so vast, why have we never detected clear signs of alien civilizations? One possible answer is that there aren't any. Not because life is rare, but because we are in a controlled simulation that doesn't include them. Just as a video game only generates what is necessary for the player's experience, our simulation may limit our knowledge of other life forms to keep the illusion intact. If we are indeed living in a simulation, the next question becomes, who created it, and for what purpose? One of the most popular explanations is that an advanced civilization in the distant future is running ancestor simulations, recreations of their past to study history or human behavior. Just as we use computer models to simulate climate patterns or economic systems, they may be running vast simulations to understand their own origins. Another theory suggests that our reality is an experiment, perhaps conducted by an unknown intelligence to observe how civilizations develop. If so, the creators might intervene in subtle ways, adjusting parameters when necessary, just as researchers manipulate variables in a controlled study. A more unsettling possibility is that our existence is simply a form of entertainment for a higher intelligence. In the same way that we create video games, virtual worlds, and AI-driven simulations for fun, a far advanced species could be running us for amusement, observing our struggles, achievements, and failures as mere spectators. If we are in a simulation, is there a way to break out of it? Some thinkers have suggested that anomalies in physics might be clues, errors or glitches in the system that could reveal the artificial nature of our reality. One bizarre proposal is that if our simulation has limitations, we might be able to hack it or trigger an event that forces the system to reveal itself. Theoretically, if we built a quantum computer powerful enough to simulate an entire universe within our own, it could cause an overload, what some call a simulation collapse, forcing the system to show its true form. However, if the simulation is designed to be self-contained, it is possible that we will never find a way to break free. The system could be built with safeguards to prevent simulated beings from realizing their nature. If the simulation hypothesis is true, it raises profound questions about the nature of existence. Does it change the meaning of life if we are simply lines of code running in an advanced program? Would it make our emotions, relationships, and experiences any less real? Some argue that even if we are in a simulation, it doesn't matter, because our experiences are still real to us. Whether or not we are living in a base reality, we still form meaningful relationships, pursue knowledge, and strive for purpose. Just as characters in a novel or game can have rich experiences within their world, so too can we, even if that world is artificial. The simulation hypothesis remains one of the most fascinating and unsettling ideas in modern science and philosophy. While we may never have definitive proof one way or another, The possibility alone forces us to reconsider everything we think we know about reality. Whether we are in a simulated world or not, the mere act of questioning it brings us closer to understanding the fundamental nature of existence. For now, we continue to search for answers, but the greatest mystery of all may be whether we are truly meant to find them, or if the creators of our reality have ensured that we never will. Chapter 8. The Heat Death of the Universe. Imagine a time so distant that even the concept of time itself loses all meaning. A point in the far, far future where everything has faded into an eternal silence. No stars, no galaxies, no warmth, no movement. This is the fate that awaits our universe according to the theory of heat death. A chilling prediction that suggests the cosmos will eventually wither into a cold, lifeless void. Unlike dramatic apocalyptic scenarios of fiery explosions or cosmic collisions, heat death is a slow, inevitable decay, an irreversible fading of all energy, all structure, and ultimately, all possibility. To understand heat death, we need to examine one of the fundamental laws of physics, the second law of thermodynamics. This law states that in any closed system, entropy, the measure of disorder, always increases over time. In simpler terms, energy tends to spread out, becoming less useful, less organized, and more evenly distributed. Just as a hot cup of coffee left in a room will eventually cool down until it matches the surrounding temperature, the universe itself is on a trajectory toward equilibrium. Right now, our universe is full of structure. Galaxies, stars, planets, and complex systems held together by gravitational forces. But over time, as energy disperses and cannot be replenished, these structures will break down, leaving only a cold, uniform expanse. The cosmos is slowly unwinding, and one day it will reach a state where no further change is possible. The process leading to heat death isn't something that will happen in our lifetimes, nor in the lifetimes of countless future civilizations. It is a fate that plays out over timescales so vast they are almost incomprehensible. Currently, the universe is still in an active and vibrant state, with new stars forming from clouds of gas. However, this process won't last forever. As time passes, galaxies will exhaust their supply of raw material needed for star formation. In about 100 trillion years, the last stars will flicker out, leaving behind only remnants, cold white dwarfs, neutron stars, and black holes. Without new stars being born, the cosmos will enter an era of darkness. Once all stars have burned out, black holes will dominate the universe. Over trillions upon trillions of years, these gravitational giants will consume whatever matter remains. But even black holes aren't eternal. According to Hawking radiation, they will slowly evaporate, emitting tiny amounts of energy until they, too, disappear. The largest black holes will take an estimated a Google years to fully evaporate, an almost inconceivable length of time. After the black holes have vanished, only the most basic particles will remain: electrons, neutrinos, and low-energy photons drifting through an ever-expanding void. No new reactions will take place because all usable energy will have been exhausted. The universe, once filled with dazzling light and unimaginable power, will be nothing more than an immense, silent abyss. At this point, the universe will have reached its final equilibrium state, maximum entropy. With no gradients of heat, no movement, and no energy to drive any process, time itself will cease to have any meaning. When there is nothing left to change, what does time even measure? the once chaotic, ever-evolving cosmos will have settled into the stillest state imaginable. Absolute and irreversible silence. Some physicists speculate that the universe might not be doomed to eternal stasis. There are theories suggesting that quantum fluctuations, random tiny events that occur in empty space, could trigger a new Big Bang, essentially rebooting the universe. Others propose that if our universe is just one of many in a vast multiverse, new universes could continuously be born while old ones fade away. However, if heat death truly is the final fate, then the universe will never experience another moment of complexity or creation again. The idea that everything, every star, every galaxy, every thought, will one day fade into an unchanging abyss is deeply unsettling. It forces us to confront the vast impermanence of existence. But perhaps there is a strange comfort in it as well. The heat death of the universe is so far in the future that it is beyond our realm of concern. We are alive in a golden age, a time when the universe is full of energy, light, and wonder. If anything, the knowledge of our universe's distant fate serves as a reminder to appreciate the present, to marvel at the complexity of existence while it lasts. For now, the cosmos is still alive, burning brightly in its billions of galaxies. But one day, the fire will go out, and the universe will finally rest in the deepest sleep imaginable, a sleep from which it may never wake. Chapter 9. The Phantom Time Hypothesis. Imagine waking up one morning to discover that everything you thought you knew about history was wrong. Not just a minor detail, but entire centuries of human civilization fabricated, inserted into the timeline like a masterful illusion. This is the unsettling premise of the Phantom Time Hypothesis, a theory that suggests a significant chunk of recorded history never actually happened. If true, this would mean that many of the events, rulers, and achievements we associate with our past are nothing more than elaborate fiction. The idea was first proposed in the 1990s by a German historian and conspiracy theorist named Herbert Illig. According to his claims, the period between 614 and 911 AD, nearly 300 years, was artificially inserted into our historical records. This would mean that the year we currently live in is not actually 2025, but rather closer to 1725. The implications of this claim are staggering. If true, much of medieval history, including the reign of Charlemagne, never actually occurred. But why would such a grand deception take place? Illig argued that the Holy Roman Emperor Otto III, along with Pope Sylvester II and the Byzantine Emperor Constantine VII, orchestrated this fabrication in order to place themselves at a more significant point in history, specifically the symbolic year 1000 AD. By manipulating calendars and records, they could present their rule as occurring at a time of great prophetic importance, thereby legitimizing their authority. The theory suggests that documents, architecture, and even scientific knowledge from this period were either misdated or deliberately forged to fit this revised timeline. At first glance, the theory may seem outlandish, but its proponents argue that several anomalies in historical records support the idea of missing or altered time. One of the primary pieces of evidence cited for the phantom time hypothesis is the apparent lack of significant archaeological finds from the early Middle Ages. Compared to other historical periods, relatively few artifacts, buildings, or manuscripts from 614 to 911 AD have been discovered. Some theorists argue that this gap suggests these centuries never actually happened, and that historians unknowingly filled in the missing time with fabricated events. Another aspect of the argument revolves around the transition from the Julian calendar to the Gregorian calendar in 1582. The Julian calendar, introduced by Julius Caesar in 45 BC, had a small miscalculation in its leap year system, causing the calendar to drift roughly one day every 128 years. By the time Pope Gregory XIII corrected this in the 16th century, one would expect a discrepancy of about 13 days. However, the adjustment only required a shift of 10 days, which some theorists claim suggests that 3 centuries were never actually experienced. Historical documents from different regions often show inconsistencies, contradictions, and overlapping chronologies. Some records from China, the Middle East, and Europe appear misaligned when compared side by side. Could this be evidence of an artificially stretched timeline? Or is it simply a result of imperfect record-keeping from a time when information traveled slowly and documentation was not standardized? While the theory raises intriguing questions, the overwhelming consensus among historians and scientists is that it is fundamentally flawed. Several key points undermine the idea that centuries of history were fabricated. One of the strongest arguments against phantom time comes from astronomy. Ancient civilizations carefully recorded celestial events such as solar eclipses, planetary alignments, and supernovae. These records, preserved independently by different cultures across the world, match modern astronomical calculations. If entire centuries were fabricated, these astronomical events would not align as perfectly as they do. The evolution of languages, architecture, and technology shows a gradual progression rather than an abrupt jump. If 3 centuries had been inserted into history, we would expect to see major inconsistencies in the development of human civilization. Instead, we observe a natural flow of progress in everything from written scripts to agricultural techniques. The phantom time hypothesis assumes a Western European conspiracy, but history is not confined to Europe alone. Byzantine, Islamic, and Chinese records all document events that overlap with the supposed missing centuries. For the theory to hold, every major civilization across the globe would have needed to conspire together to create a false timeline, an incredibly unlikely scenario. Despite the evidence against it, the phantom time hypothesis persists in certain conspiracy theory circles. Part of its appeal lies in the allure of hidden knowledge, the idea that mainstream academia has been deceived, and that only a select few can see the truth. The concept also plays into a broader fascination with revisionist history, where people question established narratives and look for alternative explanations of past events. Psychologically, the idea of time being manipulated taps into a deep human fear. The fear that reality is not what it seems. If we cannot trust the very foundation of our historical records, what else might be false? This kind of skepticism, while healthy in moderation, can sometimes lead to embracing theories that lack empirical support. While the theory itself is widely debunked, it does highlight an important point. History is never as fixed or objective as we might think. Errors, biases, and deliberate fabrications do exist within historical records, even if they don't take the form of entire centuries being erased or invented. The study of history is an ongoing process of verification, correction, and interpretation, the phantom time. Hypothesis, though flawed, serves as a reminder to always question sources, analyze evidence, and seek the most logical explanations. It invites us to think critically about how history is constructed and to appreciate the immense work historians do to piece together the past as accurately as possible. In the end, time is one of the few things we take for granted as absolute, yet even it can be called into question. While the centuries in question undoubtedly existed, the mere suggestion that they might not have forces us to reconsider how much of our understanding of reality is built on trust. And perhaps, in an age of misinformation and digital manipulation, that is a lesson worth remembering. Chapter 10: Quantum Immortality and Schrödinger's Cat. Imagine a reality where you can never truly die. No matter what happens, there is always a version of you that survives, experiencing an unbroken consciousness that stretches into eternity. This is the unsettling implication of quantum immortality, a mind-bending concept rooted in quantum mechanics that challenges everything we think we know about life, death, and existence itself. At the heart of this idea lies one of the most famous thought experiments in physics, Schrödinger's cat. Devised by physicist Erwin Schrödinger in 1935, the experiment was meant to illustrate the strange implications of quantum theory. In this scenario, a cat is placed inside a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers a mechanism that breaks the vial, releasing the poison and killing the cat. If the atom does not decay, the cat remains alive. According to the laws of quantum mechanics, until the box is opened and observed, the cat exists in a superposition, both alive and dead at the same time. While Schrödinger originally intended this paradox to highlight the absurdity of quantum mechanics, later interpretations have taken it much further. The many-worlds interpretation, first proposed by physicist Hugh Everett in 1957, suggests that every quantum event causes reality to branch into multiple parallel universes. In the case of Schrödinger's cat, one universe exists where the cat is dead, while another exists where it is alive. This concept forms the foundation of quantum immortality. Quantum immortality extends the logic of the many-worlds interpretation to human consciousness. If every event with multiple possible outcomes results in a split reality, then, in scenarios where a person might die, there must always be at least one universe where they continue to live. From a first-person perspective, you would only ever experience the realities where you survive, while other versions of you perish in separate timelines. In theory, this means that you would never encounter your own death. You would always remain in a version of reality where you are still alive, no matter how improbable that survival may be. This idea raises unsettling questions. If true, then in some version of reality, you have survived every fatal accident, every disease, every catastrophe that could have ended your existence. But there is a catch. Surviving doesn't necessarily mean thriving. If you are constantly escaping death, you may end up in increasingly unlikely and potentially horrifying states of existence, trapped, injured, or suffering indefinitely. In this sense, quantum immortality may not be a gift, but a curse. Though quantum immortality remains purely theoretical, there have been thought experiments that attempt to explore its implications. One such scenario involves a hypothetical quantum suicide experiment. Imagine a physicist sets up a machine that has a 50% chance of killing them instantly upon activation, based on the quantum state of a particle. If the many-worlds interpretation is correct, there will always be a version of the physicist who survives, no matter how many times the experiment is repeated. From their perspective, it will seem as though they are defying death again and again, while outside observers will see the majority of versions perish. While no ethical experiment could test this idea directly, it leads to deep philosophical questions about the nature of reality. If consciousness always continues along a timeline where survival is possible, does this mean that everyone is effectively immortal within their own experience? If death is never perceived, does it even truly exist? If quantum immortality applies to individuals, could it also apply to the universe itself? Some physicists speculate that if our universe faces a potential end, whether through heat death, vacuum decay, or another catastrophic event, there may always be a branch of reality where it persists. Just as an individual consciousness might always find a path to survival, perhaps the cosmos does the same, existing in an infinite loop of renewal and collapse. The idea of quantum immortality can be seen in two ways. On one hand, it suggests that death is an illusion and that consciousness will always find a way to continue. On the other hand, it implies that some version of you will persist no matter what, even if it means enduring endless suffering or surviving in increasingly improbable circumstances. Perhaps the most unsettling question of all is this: if quantum immortality is real, have you already died countless times without realizing it? And if so, what does that mean for the reality you are experiencing right now? Whatever the truth may be, one thing is certain. Quantum mechanics continues to challenge our understanding of existence in ways more profound than we can possibly imagine. Chapter 11: The End of Spacetime. Planck Star Hypothesis. We tend to think of black holes as the ultimate cosmic traps, places where matter, light, and even the fabric of reality itself disappear into an unfathomable abyss. According to classical physics, anything that crosses a black hole's event horizon is doomed, crushed into an infinitely dense singularity where the known laws of physics break down. But what if that singularity never actually forms? What if, instead, something else lurks inside, a phenomenon that challenges our entire understanding of spacetime itself? This is where the Planck star hypothesis comes into play. A black hole, at first glance, seems like a straightforward concept, an object so dense that its gravity becomes inescapable. But the problem arises when we consider what happens inside. General relativity predicts that all the matter falling into a black hole should collapse to an infinitely small point, an impossibility, since nature tends to resist infinities. This is where quantum mechanics, the governing framework of the microscopic world, enters the picture. Some physicists propose that, instead of an infinite singularity, the collapsing matter inside a black hole reaches a critical point and rebounds, forming a Planck star, a hypothetical, ultra-dense core that resists further collapse due to quantum effects. The idea suggests that black holes aren't permanent, but rather a phase in a much larger cosmic process. From our perspective, a black hole seems eternal. Any matter falling into it appears to slow down, never quite reaching the event horizon due to extreme time dilation. But what if this is just an illusion? If a Planck star forms at the core, it could eventually release all the trapped matter in an explosive event. Though, due to the time dilation near the event horizon, this process might take billions or even trillions of years as seen from the outside. From the Planck star's perspective, however, this process could happen much more quickly. This suggests that what we see as a black hole might just be a cosmic mirage, an object slowly unraveling, with information and energy leaking out at a rate so slow that we barely notice. Stephen Hawking famously predicted that black holes emit radiation, gradually evaporating over immense timescales. The Planck star model provides a compelling explanation for where this radiation comes from. Instead of information being permanently lost in a singularity, it may be preserved inside the Planck star, slowly leaking out over eons in a process that could eventually return all the black hole's contents back to the universe. If true, this would resolve one of the biggest paradoxes in physics, the black hole information paradox, by showing that information is never truly destroyed, but rather stored and gradually released. If Planck stars exist, they might reveal themselves in unexpected ways. Some theories suggest that in the final stages of black hole evaporation, when most of its mass has been radiated away, the Planck star at its core could suddenly explode in a massive burst of energy, resembling a gamma-ray burst, one of the most powerful cosmic events we observe. If future telescopes detect a pattern in these bursts that aligns with the predicted lifetime of evaporating black holes, it could provide the first indirect evidence that Planck stars are real. If black holes don't end in singularities, but instead transform into something else, what does this mean for our understanding of spacetime itself? The Planck star hypothesis suggests that the very fabric of reality isn't as rigid as we once thought. Instead of an infinite collapse, there may be a fundamental quantum limit, a boundary at which gravity and quantum mechanics fuse into something we have yet to fully understand. In this sense, Planck stars may represent a deep cosmic recycling mechanism, ensuring that no information is ever truly lost, and that even the most extreme objects in the universe obey the fundamental principles of physics. If true, then black holes aren't eternal graves, but rather the slow-burning remnants of a process that will eventually return their secrets to the cosmos. Perhaps, billions of years from now, what once seemed like the darkest voids of the universe will instead become the birthplace of something new. Chapter 12. The Ultimate Fate of the Universe. The universe is vast, seemingly endless, and constantly changing. But is there an ultimate end to everything? Will the cosmos continue expanding forever, or is there a final chapter written in the fundamental laws of physics? The answers lie in the competing theories of cosmological destiny, each offering a different version of how existence itself might conclude. For most of human history, the universe was thought to be static and unchanging. That perception was shattered in the 20th century when astronomers discovered that the universe is expanding. The further away a galaxy is, the faster it moves away from us, an observation that led to the Big Bang theory. But this discovery also raised a haunting question. If the universe is expanding, where is it heading? One crucial factor in predicting the universe's fate is entropy, the gradual increase of disorder over time. According to the second law of thermodynamics, systems naturally evolve toward states of greater entropy. The universe, as a system, is no exception. As galaxies drift apart, stars burn through their fuel, and black holes slowly evaporate, the cosmos inches closer to a state of ultimate uniformity, a scenario often referred to as heat death. Heat death is perhaps the most widely accepted theory for the ultimate fate of everything. It suggests that as stars exhaust their nuclear fuel and black holes evaporate, the universe will be left in a cold, dark, and empty state where no usable energy remains. Matter itself may decay into subatomic particles, leaving behind an endless void. Time would continue, but nothing would change. An eternal silence in which all activity ceases. This idea is based on the assumption that the universe will keep expanding indefinitely. If dark energy, the mysterious force driving the acceleration of this expansion, remains constant or grows stronger, galaxies will recede from each other at ever-increasing speeds. Eventually, even atoms and subatomic particles might be ripped apart in a phenomenon called the Big Rip, leaving behind a featureless expanse devoid of structure. Not all theories predict an eternal expansion. Some suggest that the universe's fate depends on the amount of dark matter and dark energy it contains. If there is enough mass in the universe, gravity might eventually overcome expansion and pull everything back together in a catastrophic collapse known as the Big Crunch. In this scenario, galaxies would slow their outward motion, reversing direction as gravitational attraction takes over. Stars and planets would collide, black holes would merge, and temperatures would soar to incomprehensible levels. Eventually, everything would be compressed into a singularity, a point of infinite density, much like the one thought to have preceded the Big Bang. But could this be the end, or is it simply a reset? Some theories propose that the Big Crunch might lead to another Big Bang, causing the universe to be reborn in an endless cycle of expansion and contraction, a concept known as the Big Bounce. If dark energy continues accelerating the universe's expansion, we may face an even more dramatic fate. The Big Rip proposes that not only will galaxies move apart, but so will stars within those galaxies, planets from their stars, and eventually even atoms from one another. If this process continues unchecked, spacetime itself could be torn apart, erasing all fundamental forces and rendering the universe unrecognizable. Alternatively, the Big Freeze describes a slower but equally bleak outcome. Unlike the violent tearing of the Big Rip, the universe would simply fade into nothingness as stars go dark and galaxies become unreachable. Without new energy sources, all motion would eventually stop, leaving a frozen void where the concept of time loses its meaning. Black holes might play a significant role in how the universe meets its demise. Over trillions of years, they could become the last remaining structures in the cosmos, slowly evaporating through Hawking radiation. As they vanish, they release their stored energy into space, but with no structures left to absorb it, this energy would be effectively useless. The death of the last black hole would mark one of the final milestones in the universe's journey toward total entropy. Yet, some theorists suggest that black holes might serve as escape hatches to other universes. If information is preserved within black holes, as some quantum mechanics interpretations suggest, they might act as seeds for new cosmic beginnings, pockets of reality birthed from the collapse of the old. Despite these grim predictions, there remains a possibility that something unexpected will alter the course of cosmic history. Some physicists theorize that dark energy might change over time, potentially reversing expansion or stabilizing it in a way we cannot yet foresee. There's also the tantalizing idea that our universe is only one of many, a single bubble in a vast multiverse, where different physical laws govern different realities. If true, the end of our universe might be just another chapter in an endless cosmic library. Regardless of which theory proves true, the timescales involved are incomprehensibly vast. The death of the last star is estimated to occur in about 10 to the power of 14 years. Black holes could persist for up to 10 to the power of 100 years before fully evaporating. And if the universe truly enters an eternal heat death, it will be an infinite expanse of time before anything, if anything, emerges from the void. For now, our universe is still young, teeming with life and movement. Whether it ends in fire, ice, or something beyond our comprehension, the only certainty is that its fate is tied to the same forces that brought it into existence. As we look up at the night sky, we are witnessing the slow unfolding of a grand cosmic story, one that may outlast everything we know, yet remain forever beyond our reach to witness its final page.